Kepler-22b sits approximately 635 light-years from Earth in the Cygnus constellation. To the casual observer, it represents a potential second home, a habitable exoplanet covered in oceans and possibilities. But to those of us who understand the brutal realities of orbital mechanics and aerospace engineering, it represents a problem that mocks our current existence. It is a distance so vast that it effectively acts as a quarantine for humanity. Currently, the fastest object our species has ever built is the Parker Solar Probe, which utilizes the Sun's massive gravity to reach speeds nearing 430,000 miles per hour. That is an engineering marvel. Yet even if we could sustain that record-breaking velocity indefinitely, a voyage to Kepler-22b would still take nearly 1 million years. Civilization has only existed for a fraction of that time. We would not just die of old age. Our species would likely evolve into something unrecognizable before we completed even 1% of the journey. To understand why this matters, we must confront the tyranny of the rocket equation. For decades, NASA and private entities like SpaceX have relied on chemical propulsion. While effective for reaching the Moon or Mars, chemical rockets act as a prison when we look toward the stars. They simply require too much fuel to carry the fuel needed for interstellar transit. If we are to bridge the gap to a habitable exoplanet, we do not just need a larger starship. We need a fundamental shift in our understanding of propulsion physics. In this analysis, we will dismantle the 635 light-year barrier. We will examine the engineering roadmap that takes us from the nuclear concepts of the Cold War to the theoretical manipulation of space-time itself. We will explore how Project Orion, Antimatter, and the relativistic effects of time dilation offer a mathematical, if not yet technological, path to the stars. We are not looking for science fiction. We're looking for the physics that will allow us to leave our cradle. To appreciate the sheer scale of the engineering challenge before us, we must first address the limitation that has defined the space age since its inception, the Tsiolkovsky rocket equation. For those of you who followed the Apollo program, you witnessed the Saturn V consuming millions of pounds of propellant just to reach low Earth orbit. The fundamental physics remain unchanged today. Whether it is the F-1 engines of 1969 or the Raptor engines of modern SpaceX Starship vehicles, chemical rockets rely on combustion. They are, effectively, a prison of physics. To accelerate a ship, you need fuel, but that fuel has mass, requiring even more fuel to push it. This exponential penalty means that chemical rockets will never possess the energy density required for interstellar travel. However, the solution to this propulsion bottleneck is not new. It is a chapter of history many of us lived through during the height of the Cold War. In the search for greater specific impulse or engine efficiency, NASA and the Atomic Energy Commission began exploring nuclear thermal propulsion in TP in the 1960s. By passing liquid hydrogen through a nuclear reactor core, we can achieve exhaust velocities twice that of the best chemical rockets. This technology, which resulted in the NERVA program, is currently being revitalized for missions to Mars. Yet, while NTP is an excellent ferry for the solar system, it is akin to crossing an ocean in a rowboat when facing the 635 light-year abyss to Kepler-22b. To find a true interstellar contender, we must revisit a more radical proposal from 1958, Project Orion. At a time when nuclear technology was rapidly advancing, physicists like Freeman Dyson proposed using nuclear pulse propulsion. The concept involved ejecting small nuclear directional charges behind a spacecraft and detonating them against a massive pusher plate. It sounds extreme, perhaps even reckless by modern safety standards, but the physics were sound. Analysis shows that a vehicle driven by Project Orion could theoretically achieve 5% of the speed of light, 0.05 c. In practical terms, this propulsion method would reduce the travel time to Kepler-22b from the chemically limited 900,000 years down to approximately 12,700 years. While this represents a massive improvement in engineering capability, it presents a sobering reality. 12,700 years is still vastly longer than recorded human history. Even with the raw power of the atom as conceived in the 20th century, we remain tethered to the slow lane of the galaxy. If nuclear fission, the splitting of the atom, was the breakthrough of the 20th century, then controlled nuclear fusion is the imperative of the 21st. To significantly reduce the travel time to Kepler-22b, we must graduate from the brute force of Project Orion to the continuous, high-efficiency thrust of fusion propulsion. This involves replicating the power source of the Sun itself inside a magnetic containment field. In the 1970s, the British Interplanetary Society conducted the first serious engineering study of this concept, known as Project Daedalus, by utilizing deuterium and helium-3 fuel pellets to generate inertial confinement fusion. Their analysis suggested we could achieve exhaust velocities unprecedented in human history. The engineering projections for a vessel like Daedalus, or its successor, Project Icarus, are compelling. Such a drive could theoretically accelerate a spacecraft to between 10 and 12% of the speed of light. While this velocity is staggering compared to our current chemical rockets, the tyranny of distance remains. At 12% of light speed, a voyage to Kepler-22b would still require approximately 6,000 years. We are no longer talking about geological epochs, but we are still discussing a timeline that exceeds the lifespan of all recorded human civilizations combined. To bridge this gap further, we must look toward the absolute limit of potential energy density, antimatter. In the realm of physics, matter-antimatter annihilation is the most efficient reaction possible, converting 100% of mass directly into energy, according to Einstein's E equals mc squared. The raw power is difficult to comprehend. The collision of just 1 gram of antimatter with normal matter would release energy equivalent to the atomic bomb dropped on Hiroshima. If we could harness this volatility, an antimatter-catalyzed drive could accelerate a starship to 50% of the speed of light, 0.5 c. At this velocity, the journey to Kepler-22b drops to roughly 1,270 years. However, the engineering hurdle here is not just propulsion, but production and storage. Currently, generating even a few nanograms of antimatter costs trillions of dollars, and storing it requires complex electromagnetic traps to prevent it from touching the container walls and annihilating the ship instantly. While antimatter represents the pinnacle of propulsion physics, the 1,270-year transit time suggests that simply adding more energy is not the final solution. To truly solve the problem of human interstellar travel, we must stop thinking solely about propulsion and start leveraging the fundamental laws of physics described by Albert Einstein. The first step in this paradigm shift requires us to rethink the rocket equation entirely. Instead of carrying heavy fuel, what if we left the energy source back on Earth? This is the core principle behind light sails and initiatives like Breakthrough Starshot. By utilizing massive gigawatt-class laser arrays on the ground to strike a reflective sail, we can accelerate a spacecraft to 20% of the speed of light, 0.2 c, almost instantly. While this is a viable engineering path for microprobes and unmanned exploration, the G-forces generated by such rapid acceleration would be lethal to a human crew. For a manned mission to Kepler-22b, we require a solution that respects human physiology while cheating the clock. This brings us to the most counterintuitive concept in astrophysics: time dilation. According to the theory of special relativity, time is not absolute. It is relative to velocity. The faster a vessel moves through space, the slower it moves through time compared to a stationary observer. Consider an engineering scenario known as constant 1g acceleration. If we could design a propulsion system capable of maintaining a constant thrust of 1g, equivalent to Earth's gravity, we would solve two problems simultaneously. First, the crew would experience a comfortable natural gravity environment, preventing the physiological degradation seen in long-term zero-gravity missions. Second, the cumulative speed would be staggering. By accelerating for the first half of the journey and decelerating for the second half, the spacecraft would approach 99.9% of the speed of light. Here is where the mathematics becomes profound. To the Mission Control Center on Earth, the physics dictate that the ship will take approximately 637 years to traverse the 635 light-years to Kepler-22b. However, inside the ship, the relentless velocity causes time to dilate significantly. For the astronauts on board, the entire voyage would take only about 12 to 15 years. This makes the journey survivable within a single human lifespan. But there is a heavy price for this speed. It is effectively a one-way trip through time. If the crew were to turn around and return to Earth, over 1,200 years would have passed since their departure. Every person they knew, every institution they worked for, and perhaps the civilization that built their ship would be long gone. While time dilation offers a path to survival, it imposes a terrible social cost, the complete severance of the crew from their era. To reach Kepler-22b without sacrificing centuries on Earth, we must look beyond propulsion entirely and examine the structure of the universe itself. In 1994, physicist Miguel Alcubierre proposed a theoretical framework that allows for faster-than-light travel without violating Einstein's prohibitions. This concept, known as the Alcubierre drive, suggests that instead of moving a ship through space, we might be able to move the space around the ship. The mechanism relies on the malleability of spacetime described in general relativity. By contracting the space immediately in front of the vessel and expanding the space behind it, the drive creates a wave bubble. The spacecraft would essentially ride this wave, much like a surfer on the ocean. Because the ship remains stationary relative to the space inside the bubble, the crew would experience no inertial g-forces and, most critically, no time dilation. They could travel to Kepler-22b and return, having aged at the same rate as their families back on Earth. However, transitioning this from mathematical theory to engineering reality presents the greatest challenge in modern physics. The Alcubierre metric requires a ring of negative energy or exotic matter to function, substances that have not yet been proven to exist in the quantities required, or indeed at all. While currently beyond our reach, this concept proves that the laws of physics do not strictly forbid interstellar travel. They merely demand energy sources we have yet to master. We have examined the 635 light-year journey from multiple angles. Here is what stands out: the nuclear baseline. Technologies like Project Orion prove that we could have begun the journey decades ago, reducing travel time from millions of years to roughly 12,000 years. The relativistic solution. Constant acceleration drives offer the only current mathematical path for a human crew to reach Kepler-22b within a biological lifespan, albeit at the cost of extreme time dilation. The theoretical horizon. Concepts like the Alcubierre drive suggest that the speed of light is a local speed limit, not necessarily a universal barrier, provided we can manipulate spacetime itself. If the manipulation of spacetime remains beyond our grasp, and if the sacrifice required by time dilation is deemed too great, we are left with one final engineering architecture: the generation ship. This approach accepts the tyranny of distance rather than fighting it. We would not build a sprinter, but a fortress, a self-sustaining flying city designed to survive for millennia. On these vessels, generations would be born, live, and die, passing the mission parameters down to children who will never see the Earth that launched them, nor the planet they are destined to colonize. Ultimately, Kepler-22b serves as more than just a coordinate in the Cygnus constellation. It is a forcing function for human advancement. The 635 light-year distance is not merely a barrier. It is a mandate. It challenges us to transition from a civilization that burns chemical fuel to one that masters the fundamental forces of the universe. I want to leave you with a question. that tests the limits of that ambition. If you were offered a seat on a ship using constant acceleration, a voyage that demands only 15 years of your biological life, but costs 1,200 years on Earth, would you take it? Would you trade everyone you have ever known and the entirety of the world you understand for the chance to be the first to set foot on a new world? Please share your perspective in the comments below. I am genuinely curious to see how many would accept that one-way ticket. If you found this engineering analysis valuable, I would appreciate your subscription. In our next video, we will explore the specific atmospheric conditions of Kepler-22b to understand exactly what environment awaits us upon arrival. Thank you for watching.